Today we will be talking about the second lab, which is a little bit more into charge tapes. The purpose of this lab is to build on the ideas that we formed in Lab 1, but instead of treating the charge tapes like a point charge, we will now be treating the charge tapes like a line of charges. To do so, we will use an advanced computational model to calculate a more accurate value for the charge of the tape by treating it like lines of charge. We also know that these parts of our tape are positively charged. The physics concepts involved are that we have two charged tapes repelling each other, and we also have a superposition of the electrical force and field on the charges. This includes Coulomb's law and Newton's second law. The reason that all these physics concepts come into play is that we have two charged tapes, which we qualitatively figured out were both positive by comparing them to a negatively charged pen. We also know that they are negative based on their interactions with neutral objects and the way they are attracted. When we tape one of the tapes above books and hold them in the air and then put another tape underneath it, it repels the other tape, so we know that they are both positively charged. Also, these are now in equilibrium, so the sum of the forces all equal 0. Now that we have observed these ideals, and we know that the sum of the forces equals 0, so force of gravity equals 0 and electric force equals 0, we can take into idea of the mass of the tape, the distance between the two tapes, and the length of the tapes. So now that we know we have these observations from our lab, we are able to make calculations to figure out the charge of the tapes based as a line using a computational model. To do this, we will also assume that no air resistance is involved and each U-tape has the same amount of charge evenly distributed throughout its length. Going from Lab 1 to Lab 2, we will use the same calculations where we found the net charge on tape V by setting equal the electric force and gravitational force since it is in equilibrium. We also do this to find the charge of the tape when comparing it to a point charge. Using this charge, we are able to input this into our Lab 2 code, which finds the charge of the tape as a line of charges. To do this, we will make a function for electric field within our code. This function uses input charge particles and location, and then we find a distance between the two, and then find the r hat of that, which is just a square root of the distance squared. Then we put that into the electric field equation, or Coulomb's law, which is the 1 over epsilon pi naught times q over r magnitude squared times r hat to find our electric field. Next, we will iterate this value through each piece of tape by finding E field and each force for each part. At the end, we will put this also into an arrow. And now we will have the electric force of the tape on top from the electric force on bottom. Now that we have the electric force of the tape on top, we will sum that all together to find the magnitude of the vector. This magnitude is the magnitude of the charge on the tape when treating it like a line of charges. In the picture on the right, we see what the code outputs. The green arrows are the different charges throughout the line of the tape. We also have found that at the bottom, the magnitude of the gravitational force is 1.6 times 10 to the third. Also, with the big white arrow, which is electric force overall, and the big yellow arrow, which is gravitational force overall, those equal out, which put our system in equilibrium. This brings us to the final concerns of the lab. So what if you had modeled each of your tapes as a single point charge, like in the previous lab? This would have decreased the charge of the tapes by a factor of 1 times 10 to the negative fifth. We have found this factor by dividing them and seeing their differences. Since the original charge, when treating it as a point charge, was times 10 to the negative ninth, when this is the same thing times 10 to the negative fourth, we have now found that there is this factor that increases it. So why do these estimates differ? Which value is more likely to be closer to the real value? They are not the same, since a point charge is going to react differently within physics and then a line of charges. And the way they react with their surroundings and the way they react with other charges is changed, so their values are going to change. The line of charges is going to be more accurate because a piece of tape is not just one point, it is a line of charges across the entire tape. So this value is going to be much more accurate to reality than the original value.